Welcome, everybody, to the seminar. Today's speaker is Guram Bezhanishvili from New Mexico State University, and he will speak about varieties of Heyting algebras, what we still don't know. Okay, Guram.
Thank you. Thank you for having me, Keith and everyone. It's a pleasure to be here. Before we get started, I want to say just two quick things. One is that some people prefer that the questions are asked after they finish their talk. I'm not one of those. Please feel free to interrupt me at any moment. And I'll try to keep track of the chat, but if I miss something in the chat, please point out to me that there's a question there. And then another is that it's always good to have some pictures. And then I did draw some pictures, but they are on my iPad. And so once the time comes for the picture, I'm going to have to switch, because I didn't find a convenient way, to combine the two. So I have my slides on my computer, but then I'll be switching back and forth between my iPad and my computer. So please bear with me. Okay, so now with that said, as Keith said, this is a talk about Heyting algebras, more specifically about varieties of Heyting algebras. So I roughly have 22 slides. So if I spend 2 minutes on each, I should be done in 45 minutes. So let's get started. What is a Heyting algebra? Probably most of you are familiar that this is a very special distributive lattice. It's a distributive lattice such that the mean operation has a residual, and having a residual means that this property here is satisfied. Heyting algebras are non-symmetric objects, right? And then we're going to see during the talk, where this non-symmetry is coming from. One thing that I won't be saying too much about is that it's not clear from this definition that Heyting algebras are equationally definable, but it's a well-known fact that you can actually axiomatize this property by a set of equations, finitely many. Actually, you can do it with 3. And then what you get is that Heyting algebras form an equationally definable class, and hence they are a variety. So they are closed under homomorphic images, subalgebras, and products. And like I said, they are rather non-symmetric objects. Let's see where this non-symmetry is coming from. So I have some examples for you here. I consider the most standard, there are 2 examples that I consider most standard. The first one is the Lindenbaum algebra of the intuitionistic calculus. And now this actually turns out to be isomorphic to the free Heyting algebra on omega many generators, and hence it's a representative example because it generates the variety of all Heyting algebras. And you can also start talking about not just the intuitionistic logic, but you can start talking about the so-called intermediate logics. This name comes from the Japanese school back in the 50s. Umezawa introduced this term of an intermediate logic. The name comes from the fact that these are exactly the logics that are situated between the intuitionistic calculus and the classical calculus. And now you can play the same game. You can take the Lindenbaum algebra of any intermediate logic, and again, you get a Heyting algebra. And in fact, what happens is that the lattice of this intermediate logics is isomorphic to the lattice of varieties of Heyting algebras. And so you can think about these things 2 ways. One way you can think of this result as the fact that the language of intermediate logics is the right language to talk about Heyting algebras. Or else you can think about it from the other perspective, that Heyting algebras are the right models of intuitionistic logic. And this is what has been at the heart of the study of intermediate logics, starting from the 50s, that Heyting algebras were used, to investigate the complicated structure of intermediate logics. That's one of the reasons that Heyting algebras have been studied so extensively. Another comes from topology. And this is the second standard example, in my opinion. So you can look at all opens of a topological space, and then the same way that the power set forms a typical example of a Boolean algebra, opens form a typical example of a Heyting algebra. And what you need to do is, if you look at this formula right here, you need to define implication the right way. So what's here in the parentheses is the standard way how you define classical implication, but now this is intuitionistic implications. So you have to slap it with the interior operator. And so that's how you can think of a Heyting algebra, as opens of a topological space. And that's another reason why Heyting algebras are non-symmetric objects, because opens are, unlike the whole power set, which is a pretty symmetric structure, opens are less. So if you turn opens upside down, you get closed. And so what you get is no longer a Heyting algebra. Another standard example is what logicians like to call Kripke semantics. But this is really a particular example of topology, because you can think of Kripke frames as for Heyting algebras, for intuitionistic logic as partially ordered sets, PALS sets, and then taking all opposites amounts to taking open sets of the specific topology that comes from partial order. These are the so-called Alexandrov spaces. And you can think of Kripke semantics of intuitionistic logic as just a particular case of this topological semantics. And so this the second example is a particular case of the first. Here's a more general example, right? So you can take an arbitrary complete lattice, and then you can demand this join infinite distributive law that this law holds here. And then what you get is exactly complete Heyting algebra, and every complete Heyting algebra comes about that way. And so that again indicates the non-symmetry of Heyting algebras, because if you take the other infinite law, where you replace this finite mid with finite join, and then this infinite join with infinite mid, then that second infinite law may not hold in Heyting algebras. So that's another source of non-symmetry. Now, Heyting algebras also pop up in domain theory because domain theory, among other things, studies continuous lattices. And these continuous lattices, if you throw in also distributivity, then they again turn out to be Heyting algebras, more specifically complete Heyting algebras. Topos theory is another example, because if you take a topos and if you take the subobject classifier of an arbitrary topos, then that always forms a Heyting algebra. And until, I don't know the very latest couple of months, but until very recently, it remained an outstanding open problem whether every Heyting algebra can be realized that way. In universal algebra, they also pop up, because if you take an arbitrary congruence lattice, that's always an algebraic lattice. Now, if you're in a congruence distributive variety, then this algebraic lattice happens to be distributive, and hence a complete Heyting algebra. And so all these congruence lattices of algebras in congruence distributive varieties are also Heyting algebras. And there are many other examples, but that's probably enough, to give you an idea that Heyting algebras, they show up in different areas. Now, this example, this topology example right here, is, like I said, motivating example for many things, because you can think of Heyting algebras as being fixed points. I mean, Heyting algebras coming from topology, they're exactly the fixed points of the interior operator on the power set. And this idea was taken by McKinsey and Tarski in 1940s, and they ran away with it by introducing this concept of interior operator on an arbitrary Boolean algebra. And this is the direction that connects Heyting algebras with modal logic. So what you do is that you just take an interior operator on a Boolean algebra, and then you look at fixed points. And in the same way, this is just a generalization of this example I talked about opens of a topological space. Then you get that you're hiding fixed points of any interior operator on a Boolean algebra form a Heyting algebra. But now, and moreover, okay, so these fixed points, they always form a bounded sublattice. And then this bounded sublattice is a Heyting algebra if and only if this embedding has a right adjoint. And this box here is this interior operator is exactly this right adjoint, right? And what happens is that every Heyting algebra, as we will see in a little bit, every Heyting algebra is going to arise this way. And this also shows the non-symmetry because, again, you are talking about fixed points of an interior operator. And so these are non-symmetric objects. Now, okay, so now I'm going to introduce this notation. IA will stand for the variety of interior algebras. Now, what are these? These are Boolean algebras with this interior operator on them. And then now what happens is that once you take fixed points of every interior algebra, what you get is a Heyting algebra, and this extends to a functor that I call F here, from interior algebras to Heyting algebras. And now comes an interesting observation that this functor has a left adjoint. What that means is that with each Heyting algebra, you can associate an interior algebra whose fixed points are going to be isomorphic to the Heyting algebra you started with. And the construction is simply taking the so-called Boolean envelope, which is the free Boolean algebra over a distributive lattice that you start with. And then what happens is that once you take this free Boolean extension, then you have this conjunctive normal form. Every element in this free Boolean extension you can write in this conjunctive normal form. And then now you can define your interior operator on your Boolean algebra as follows. Look what's here in the parentheses. In the parentheses, what you have is classical implication. And now what you're doing is that you're replacing the classical implication by intuitionistic implication. And then you are meeting it over whatever meet you have here. And so that's how you can define an interior operator on your free Boolean extension. And then what happens is that the fixed points of this interior operator exactly going to give you your Heyting algebra back up to isomorphism, and this defines the left adjoint. And so we have this nice situation. I'm calling it modal companions. The language I'm using is the language of modal logic, but you can, of course, sell all of this purely in the language of varieties, how varieties of interior algebras and varieties of Heyting algebras correspond to each other. So if you pick an arbitrary variety U of interior algebras, then with each interior algebra in that variety, you can associate its fixed points, and that defines a variety of Heyting algebras. What is going on here? Now, what happens in the other direction? Now, suppose you pick an arbitrary variety of Heyting algebras. I'm going to call a variety of modal algebras its modal companion if it so happens that when you apply F to that variety, you pick up your U. Now, each variety of Heyting algebras may have many modal companions. What's interesting is that there's always the least and the greatest. So the greatest one, I mean, this is really related to what in logic is called the Gödel translation of intuitionistic logic into modal logic. What Gödel translation algebraically does is that it basically takes your variety of Heyting algebras and it associates with the largest variety of these interior algebras whose F image is this variety. And then what you can do, you can also associate the least variety in the following way. Remember, we have this left adjoint. Now, what we can do is that we can, with each Heyting algebra in our variety V, we can associate the corresponding Boolean envelope. We can take L of A, and we can take all these algebras arise in this way. This is not in general a variety because it may not be closed under products, but then you can close it under products and obtain a variety that way. So I'll call it L star because it's not exactly L. And then what happens is that this L star turns out to be the least modal companion of V. And so let me quickly switch to my iPad and show you the picture, because I think that this picture is going to communicate exactly what's going on with how the situation looks like. Do you guys see my my screen?
Yes.
Okay. So this picture communicates hopefully well what's really going on here. So here's the largest variety of Heyting algebras, and here's the least variety, non-trivial variety, which is the variety of Boolean algebras, and say this is an arbitrary variety here, V. Now, what's going on here? And here are all these varieties of interior algebras. Here's the largest one. And here's what's going on. If you pick an arbitrary variety of Heyting algebras, this interval here, that's the interval of all possible varieties of interior algebras that correspond, that are model companions of this one. Here's the largest one. That's obtained by taking this Gödel translation of the corresponding logic. And here's the least one. And so what these Heyting algebras give you, they provide the right tool to put some structure on these varieties of interior algebras. And so this is one way you can use these varieties of Heyting algebras to put some order on this complicated structure of varieties of interior algebras. So this picture communicates to you what's really going on. And like I said, these largest guys, they are obtained, if you start asking some computational questions, well, how do you axiomatize these things? These things you can axiomatize using this Gödel translation. Now, a natural question, and observe that I didn't give any names here. The natural question is, how do you axiomatize these things, right? And so this is going to be the next 5 minutes of the talk. Now, let me go back to my other slides. Okay, so now that we have this general picture of how things work, now I want to talk about how we axiomatize these least companions. And interestingly enough, this is related to an old problem of Hausdorff residues that go back to 1914 when Hausdorff first published his famous book on set theory and topology, right? So what is this Hausdorff residue? The Hausdorff residue is this combination. If you pick, and you can think in terms of a topological space, but more generally, you can define this in any interior algebra. So what happens is the following, that this is the combination that Hausdorff defined. This is what's known as Hausdorff residue. And basically what it does is that you can, in order to give you intuition, think about derived set, right? And so think about limit points. And you can think as follows, you can take an arbitrary set in a topological space and take all its limit points. Roughly, that's what this rho of A is. It's really bigger, but not exactly that, but that gives you an intuition. And so now I want to talk about the cyclic elements, because now you can repeat this Hausdorff residue over and over again. And it could happen like when you work with limit points, that after a while, you just stop, right? So you don't get smaller and smaller, you kind of cycle, with once you get a dense in itself space, right? And the same thing can happen here. So we can call an element a cyclic element, if after some while, there's this Hausdorff residue that doesn't produce anything new. And, some of you might have heard the name of Zhigorchik. He was a well-known logician, and mathematician, who did some important work in topology and also in constructive mathematics. So because of the system that he introduced, I'm going to call these algebras an interior algebraic Zhigorchik algebra if we don't have these cyclic elements. So in terms of topology, you can think that no matter what subset you pick, eventually, you get down to empty, right? So you don't cycle ever, right? So why am I saying all of this, right? Because it's exactly this Zhigorchik's axiom, not having cyclic elements, that it corresponds to these least model companions, right? So these least model companions turn out to be exactly these varieties of interior algebras which satisfy this additional property of being a Zhigorchik algebra. And so then this least companion is the greatest companion is basically your Gödel translation. It's axiomatized by taking the Gödel translation of the axioms, axiomatizing your variety. And then the least one is axiomatized by throwing in also this Dvořák's axiom. And here comes this famous Bloch-Esakia theorem from the 70s that says that actually this is an isomorphism. This is an isomorphism of lattices. So let me do another picture here to give you an idea of what's really going on. That and I apologize for going back and forth between the screens. But so here's the let's see if it shows up right there. So here's really, you know, again, the same picture, but looked at it from a slightly different perspective. Here are your varieties of Heyting algebras. And now, you know, now I'm giving this name. This is the Dvořák algebra. So this is all possible companions of our Heyting algebras. I want to take the least. Every time I want to take the least, if I take the least ones, then this is what I'm picking up. And this lattice is going to be isomorphic to this lattice. And algebraically, it's exactly this L star that produces this, what I call this Bloch-Esakia isomorphism. So that's really this connection between interior algebras and Heyting algebras, or rather varieties of interior algebras and Heyting algebras, that actually culminates in this result known as the Bloch-Esakia isomorphism. Okay, so, but this is really about using the machinery of Heyting algebras to put some structure on the varieties of interior algebras. So that's really how you can use Heyting algebras for the study of interior algebras. But what about the study of Heyting algebras on their own? What can we say there? Which screen are you seeing, guys, now? Are you seeing my computer or my iPad?
Tablet.
Oh, you're seeing my tablet?
Picture on the tablet, yeah.
My bad. Let me do it again. Thank you, Keith.
Yeah.
What about now?
Yeah, this is your computer.
Thank you. Okay. So now let's go back to the study of Heyting algebras. And so one of the main tools is duality theory here, right? So as you all know, duality theory goes back to the 30s, when Stone did his fundamental work. And then in the 70s, Priestley developed this alternative way, or generalized Stone duality, to what we now call this Priestley duality for distributive lattices. And in particular, since every Heyting algebra is a distributive lattice, you can apply Priestley duality to Heyting algebras. And the result is what's known as Esakia duality. And so what happens is that there's additional property that the Priestley topology or Priestley space. So this is how Priestley duality works, right? You start from your distributive lattice, then you define the Stone topology on it, and then the Stone topology satisfies this additional interaction, and you also have your order, which is inclusion on prime filters, and this Priestley separation axiom is satisfied. So really what we're having is this Stone space, which is ordered and has this additional feature that Priestley separation holds. But then what distinguishes the fact that the lattice we started with is a Heyting algebra? What distinguishes it is that it's a continuous relation. And what it means to be continuous relation is that the downset of each clopen has to be clopen, or if you prefer to speak in terms of the Viatori space, really what it means is that this natural map into the Viatori space is a well-defined continuous map. And then what we get is that, so that's what an Esakia space is, right? An Esakia space is a Stone space such that the order on the Stone space is a continuous order, or in other words, it's a good Priestley space, so to speak, right? And then an Esakia morphism is a continuous map that works well with the order, right? So these are the so-called p-morphism condition in modal logic that pops up also here. And then we get this Esakia duality, that the category of Heyting algebras is dually equivalent to the category of Esakia spaces. And so you can use these Esaki spaces as a tool, to study Heyting algebras. And that's a very useful tool. Now, how does that relate to this famous Johnson-Tarski duality for modal algebras in general and for interior algebras in particular? You can play the same game. Johnson and Tarski back in the 50s, extended this stone duality to cover also these modal operators on Boolean algebras. In particular, that modal operator can be an interior operator. And then what you do is that you get this, once it's an interior operator, then the relation that you get on the dual space becomes a continuous relation. And so what's happening here is that previously I had partially ordered Esaki spaces were partially ordered stone spaces where the partial order was continuous relation. Now I'm getting pre-ordered or quasi-ordered, whichever you like better, stone spaces where this pre-order is continuous relation. So the two are very closely related. So interior algebras are more general structures. And from the point of view of duality theory, they manifest themselves in the following fact that partial order that you have for Heyting algebras has to be generalized to pre-order, right? And so we call an interior algebra a skeletal algebra if that pre-order, if the fixed points generate the Boolean algebra, which dually means that the pre-order is actually a partial order. So that's how the two are related, and so then we get this variety. It's not a variety. We get this category of skeletal algebras. And that skeletal algebras now becomes equivalent to Heyting algebras because dually they are exactly the same thing, right? So this pre-order now in skeletal algebras becomes a partial order. And the two things are the same. But here's an important observation that the skeletal algebras, they don't form a variety, actually. They are not closed under products. What's actually happening is that it's always this skeletal algebras in each variety of Zhigorchik algebras that actually generate your variety, and that's the so-called Bloch's lemma, which is behind this Bloch-Esaki theorem. And so this is an interesting example of two categories being equivalent, one of them being a variety, like Heyting algebras, and the other not a variety. I think that there were some studies, I remember in particular one paper by Mackenzie from the 90s, where he studied what it means, that you have two categories that are equivalent, one of which is a variety, but the other isn't, right? And so this is a typical example of such a situation. Okay, so now I'm halfway through. So now what I want to talk about is the so-called Hosoi slices. Now I want to use this Esakia machinery or Esakia duality as a machinery to put actually some order on the varieties of Heyting algebras and see what kind of situation we get here, right? So Hosoi was another representative of this Japanese school of logic. These slices that he introduced, they date back to the 60s. He didn't do it this way, the way that I'm going to present it, but this is really what it amounts to in the language of prime spectra of Heyting algebra. So pick an arbitrary Heyting algebra and take its prime spectrum, and you just look at maximal chains that you get there. So it's similar to this crude dimension in algebra, right? And so, if it's finite, then you're going to be in a finite slice, so to speak. And if it's infinite, then you're going to be in an infinite slice, right? Now, what's interesting and of note is that these slices provide classification of all possible varieties of Heyting algebras. And this is what we call this Hosoi slices. And each slice is going to have the least element and the greatest element. And so the least element is going to be this variety generated by all chains of length no more than, well, maybe just one is enough. Just take this one chain and generate the variety by it. That's going to be your least element in the slice. And the greatest element is going to be take all Heyting algebras that have this property that their length, if you look at the spectrum, then the maximal length are restricted by n. So here comes another picture. I think that everything that I say on this slide is going to be much better understood if I do this. Okay, so now you should see my iPad, right? And so this is really the structure of all varieties of Heyting algebras. So here's all Heyting algebras. This is the Boolean algebras, which is the same as the variety generated by the two-element Boolean algebra. And here are my chains. So this is the variety generated by the three-element chain. This is the variety generated by four-element chain. This is the variety generated by n+1 element chain. This is the variety generated by all chains. This is slice 2. So these are all the varieties which have this property that their maximal spectra are, they don't get higher than 2. Here's the largest one. Here, the height of 3 or depth 3, this is the largest one. And so this is how you get these chains, right? So, so this is the picture you want to keep in mind when you think about varieties of Heyting algebras. Now, let me tell you more. Let me stop sharing this and let me tell you more. Oh, and by the way, so this C infinity, which is this guy here, it's the join of all those guys. And then it's generated by all chains or by finite chain. Oops, what did I do? All chains, all by finite chains, you know, so, and also this guy, I should probably call HA infinity because it's the join of all these guys. And so it's really, you know, generated by all finite Heyting algebras. Now, let me tell you more about these slices. I don't think that I shared the right thing. Here it is. Okay. So now let's move forward. I didn't even bother to draw this S0 because this S0 just has trivial variety, so you can ignore that. S1, I already told you, you know, it's just Boolean algebras. You know, Boolean algebras, that's the only variety, you know, that if you take the spectra of Boolean algebras, they are just of height 1, you know, they're all max ultra filters, you know, there's no order on them, you know. S2 happens to be countable, and I'll tell you exactly what the structure of S2 is. Here's the, I'll show a picture of this, but here's an interesting fact. Look at this last bullet, you know, starting from 3, all these slices become uncountable. So it's a very, very complex structure that we're talking about here. But slice 2 is pretty easy to get a handle of, right? All you have to do is just to take this 2 to the power n as your classic Boolean algebra, add a new top to it, and that's what it's gonna, so let me do a picture because it's gonna give you a better idea. I have it right here. Here. So here's my picture, right? So this picture is going to tell you a lot more than everything else I have on the slides, right? So here's what's going on here, right? So you take the 2-element Boolean algebra, you put a new top on it. Here you take 4-element Boolean algebra, you put a new top of it. Now, what did you do here? The 2-element Boolean algebra, the spectrum of it is just 1 point. And you just, 1 point, and you just add a new bottom to it. Here, the spectrum of this is these 2 points. And because of this, you're adding a new bottom to it. Same here, you take this 2 to the power n, this is the spectrum of it. And you're putting a new bottom right here because of this prime filter here, right? And so dually, you know, these are the guys, you know, and so V1 is generated by this algebra, V2 is generated by this algebra, Vn is generated by this, and then here you have the one that is generated by all of those, right? It is the join of those, right? And so if you look at, so this is the bottom of your picture, right? So here you have Boolean algebras. This is your countable chain that we get here. It's this chain right here. But then starting from here, life gets more complicated. Okay, so now back to this other picture. Or rather back to my slides. So this is the general idea that's been how these varieties look like, right? Now, what are the problems, that people tackled, some successfully, some less so? Call a variety of finite depth if it's in one of these finite slices, right? So it turns out that these are all locally finite. Now, the natural question arises, are these the only locally finite ones? Well, the question is no, because if you take all chains, it's easy to prove that the variety of all chains is also locally finite. This remains open. I mean, it's been open for a long time, right? For a while, to characterize which varieties of Heyting algebras are locally finite. For a while, this was a conjecture. I think that in early 2000s, people started to think, maybe already in the 90s, that maybe this is what's happening. I mean, the free one-generated ones don't decide everything. That was known since this. The free one-generated one is this famous Rieger-Nishimura lattice that I didn't draw here, because most of you are probably familiar with it, But starting from two generated, things become much more complicated. There's this famous result of Mardaev. Mardaev was remember, maybe I haven't mentioned the name yet, but Mardaev was representative of Soviet school of model logic in the 80s and 90s. I was told that he passed away recently, so there's a very interesting result called what I call this Mardaev's theorem that Mardaev proved in the 80s. I think that 86 or 87 is the year. It is about Brauerian algebras. What is a Brauerian algebra? It's the same as Heyting algebra, but you may not have bottom in the signature. Heyting algebras always have bottom because bottom is needed to talk about intuitionistic negation. So if you don't have intuitionistic negation, then what you get is what people call these Brauerian algebras, right? And Mardaev proved this very surprising result that two generated Brauerian algebras determine everything, because every n generated one you can embed. But the embedding doesn't preserve zero. And unfortunately, this result cannot be used to prove that two generated Heyting algebras decide everything in varieties. They decide local finiteness in varieties of Heyting algebras. And now we have evidence that this is probably not true. Probably this problem is going to stay unresolved, because there's an evidence that you can build for every n, finite n, you can build a variety of Heyting algebras where all n generated ones are finite, but n plus one generated ones are already infinite, So things are very different from what happens on the other side, on the side of interior algebras, because in interior algebras, because our language is more expressive, being locally finite is simply decided by being of finite depth. So this is this well-known Segerbert-Maximova theorem from 1970s. And by the way, Mardaev was a student of Maximova. Okay, so I wanted to mention this open problem because it bothered me for a long time, right? And so I wanted to mention it to you. Now, there are some other. So this is one of those problems that in my abstract, I said that it continues fighting back, right? So this one in particular continues fighting back really hard. There are some others, and I want to finish my talk with some others. So this is known, what I'll talk next is what's known as Kuznetsov's hierarchy. And really, this is something that is very well known to people in universal algebra, but Kuznetsov did that from the point of view of logics, but I'm going to present it from the point of view of varieties. So he started to put some kind of order, on different intermediate logics, and he said the strongest ones are the so-called logics that are tabular, that there's one table, like classical logic, you take this table consisting of just 0 and 1, and that determines your logic. So in terms of algebras, these correspond to finitely generated varieties. So these are the bottom. So the picture changes upside down, right? So these are the bottom ones, right? And then the next stage is the locally finite ones. These are the locally tabular ones in the language of Kuznetsov, right? The next ones are the ones that are generated by finite. Clearly, it's a classic result. I think it goes back to, I don't know, 60s, maybe even earlier, that every finitely generated variety is locally finite, right? So this class FG is contained in LF. And then bigger class is those varieties that are generated by finite algebras. These are, in logic, these are called logics with FMP. So I'm using this FMP for that. And now observe that these finite algebras, they are exactly offsets of finite posets. So the next one in the hierarchy is what they call, that's what people call Kripke completeness, right? From the point of view, logicians call these logics being Kripke complete. From the point of view of universal algebra, what we're talking about is varieties that are generated by algebras of this form. If X is finite, then that's exactly what you get here. But X might be infinite now. And so there's this concept of Kripke completeness, which is a bigger. And then, as I said, these Kripke algebras coming from Kripke are special case of the algebras coming from topology. And so you can talk about topological completeness. So that's what I denote by top here. And more generally, you can talk about what I denote by CHA. These are varieties that are generated by complete Heyting algebras. So remember, every topology is a complete Heyting algebra. It's even more, right? It's a special complete Heyting algebra. And every topology of this form, that's also a complete Heyting algebra, right? And so we get this hierarchy that finitely generated ones are contained in locally finite ones. It's easy to give an example that this inclusion is proper. This inclusion is also proper, also not difficult. This inclusion is also proper, slightly more difficult. But now here I'm not saying anything, right? Because we don't know. We have inclusion, all right, but we don't know whether this is proper or not. To this day, and this we don't know. So here are some problems that keep fighting back. We don't know if there exist varieties of Heyting algebras that are generated by algebras coming from topologies, but are not generated by algebras coming from Kripke frames. And there's this famous Kuznetsov's open problem that's been open since 1975. If there exist varieties of Heyting algebras that are not generated by that, or there exist logics that are topologically incomplete, is there a variety of Heyting algebras that is not generated by the algebras that come from topologies? And it is also open whether there exist varieties that are not generated by their complete members, right? Now, we do have a little bit, as in the case of locally finite varieties, that there was some progress, but that one was a negative progress, right? So here we have a little bit of positive progress, right? And so I want to finish my talk giving you some positive progress in these directions, right? Well, first of all, what was known, so the signature of interior algebras, and in particular in modal algebras in general, you have a richer language, right? So these things you can distinguish there. In particular, Kuznetsov's problem has a negative solution for varieties of interior algebras. That was known from the 80s, but then not very much progress was done about varieties of Heyting algebras. So there's a little bit of progress that I want to report now. There's this notion of bi-Heyting algebra. Now, remember that when I started my talk, I said that Heyting algebras are highly non-symmetric objects. In particular, if you take a Heyting algebra and put it upside down, if you take order dual, that's no longer a Heyting algebra. Well, call a Heyting algebra a bi-Heyting algebra if it so happens that when you put it upside down, it's a Heyting algebra. So these are more symmetric guys, right? And so that helped, right? So being more symmetric helped in resolving Kuznetsov's problem in the negative, right? So in the varieties of bi-Heyting algebras, Kuznetsov's problem has a negative solution, right? So there exists a variety of bi-Heyting algebras that is not topologically complete, right? So that what that means is that there exist varieties of Heyting algebras that are not generated by complete bi-Heyting algebras. This bi is critical here, right? We cannot take this bi off. If you take bi off, you've resolved Kuznetsov's open problem, but that remains still, that's the part that is still fighting back pretty hard. And unfortunately, the evidence is that we're gonna need new machinery. The machinery that we have so far doesn't seem to be able to resolve this. Okay, so I still have 5 minutes, right? So one more that if nothing else, this is worth mentioning because I want to advertise an old result of blog that some people might not know. So given a property, you can always talk about the degree of that property in the class that you're interested in, the lattice that you're interested in, right? So you can have for example, completeness and incompleteness that are fundamental concepts in logic, right? So once you have the notion of completeness, you can talk, or the notion of incompleteness, you can talk about the degree of it, right? So if you take a logic and if you look at its Kripke frames, then you might wonder, are there other logics that share exactly the same Kripke frames with it? So this is this famous degree of Kripke incompleteness. And Fine in the 70s asked this question. Once it became clear that there exist varieties of modal algebras that are not generated by their Kripke algebras coming from Kripke frames, Fine asked, can we at least, characterize the degree of incompleteness of a given logic? And here comes this famous Bloch's dichotomy theorem that was proved in 78. And there's a famous story about it that I want to tell that it's very surprising what Bloch proved. Bloch proved that if you pick an arbitrary logic, that always its degree is either 1 or continuum. It is 1 exactly when it's, those of you who are familiar with the technique of splittings in universal algebra, it's going to be 1 exactly if it's join, if the logic is really the join of the splitting variety, or the algebra is the axiom, or the corresponding variety is axiomatized by these formulas that come from the splitting. So it's a joint splitting variety, And then otherwise, its degree is going to be continuum. And this is one of these results that now you can find in books on modal logic, but this was never published. The reason this was never published is because when Bob Bloch actually submitted this manuscript in a top journal, the referee said that he couldn't find a mistake in the proof, but he couldn't believe that this is true. He just couldn't believe that such a nice characterization was possible. And so then that was the time when Bloch finished his PhD, and he was now switching from modal logic to universal algebra. And he basically said, okay, if the referee doesn't believe me, fine. I'm going to keep it as a manuscript, and then move on and do other things, right? And then, of course, the result checks out. And now you can open a book on modal logic and find this Bloch's dichotomy theorem there. But it's interesting that this was never actually, the proof was never actually published. This remains this ILLC report. ILLC is this Institute of Logic, Language of Computation of University of Amsterdam, and it remains a technical report there. Now, why am I mentioning all of this, right? Because we could ask the same question for Heyting algebras, right? Now, we do know that there's continuum many of Kripke incomplete varieties of Heyting algebras, but we know little about the degree of Kripke incompleteness there. However, there's evidence that things are different. And the reason that we believe that things are different is the following, because we could ask the same question by replacing Kripke with finite modal properties. So you could ask the same, take a variety of Heyting algebras, look at its finite members, and now ask the question, how many varieties there are that share the same finite members with this variety? If Bloch's dichotomy was true, there would be either 1 in the case it's joint splitting or continuum many. But that's not the case. This is the latest that I wanted to actually report on, right? That whatever countable cardinal you give me, I can find you a variety that's going to have the degree exactly that kappa. And if you assume continuum hypothesis, which tells you that there are no other cardinals between countable and uncountable, then these are going to be, every one of those is going to be realized. And because the blocks dichotomy also works for varieties of interior algebras for FM, if you replace incompleteness with FMP, if I had to make a conjecture, I would bet that this anti-dichotomy theorem is also going to be true for the question for Kripke incompleteness for varieties of Heyting algebras. But that's pure speculation at this stage because we don't have sufficient machinery for that. Anyway, hopefully this gives you some rough idea, what people in this area do. And well, thank you very much.